Okay, remember in the last video I mentioned to you that in mathematics in general there are lots of ways to try to get solutions of mathematical problems. One way is to actually work through the formulas and the equations, and you solve it by working through the symbols and such, and using different techniques, and that's all called the analytical way. You analyze. Okay, and so that's kind of the most standard approach, and nothing wrong with that at all. But sometimes it can't be done, or sometimes even if it can be, there's still other ways to get other insights that might not show up there. And so another technique which is used is to use graphs to get solutions of mathematical problems. And yet another way is to do it numerically, and to just stick numbers into a calculator, or if they're simple enough you can figure them out by hand, but those are different ways. Yet another way is sometimes said verbally, but I'm not sure if there's a way to actually solve it, unless it's just a matter of solving it by thinking it through with words. Sometimes actually there's some things in mathematics that are easier understood in words than it is in symbols. For example, De Morgan's law says that the intersection of the unions is the union of the intersections. So if you hear it like that, it's actually easier to understand than if you see a bunch of symbols. But anyway, so this is verbally. So just as an example, when I teach my calculus students that the limit of the sine of theta over theta as theta goes to 0 is equal to 1, there are lots of ways you can do it. You can do it analytically by actually going through a proof. I won't even touch that one. That takes a little while. But another way is to think about it graphically. If you have the unit circle, there's the unit circle right there, which means the radius is equal to 1. And recall that the arc length of a circle is the radius times the angle. So if you have a unit circle, then the angle and the arc length are the same. So here this is 1, and if this right here is theta, then by definition this length right there is the sine of theta, and this length right there is the same as this, so this length right there is theta. So there's sine of theta and there's theta, and you can see that they're kind of close to the same length, right? See that? This length and this length. And in particular, if you get smaller and smaller angles, then you see that this length and this length, even though they're both getting small, they're also getting closer. The ratio is getting closer and closer together. See that? Those two lengths are getting closer and closer together. As you get even to a smaller angle, those two lengths become more and more the same. So there's a way to do it graphically. Another way to do it graphically is if you knew what the graph of the sine of x was. There's the graph of the sine of x, and here's the graph of the line y equal x right there. And those two graphs come in right along the same line as you approach 0. So there again, you see that the ratio is close to 1. And finally, another way is just to take your calculator and make sure it's in radian mode, and put in values that are really close to 0. And if you do, then your calculator will give you a ratio really close to 1 there. So there's just another example of where you use all these different methods, and by using them all, you get a better sense. Certainly, I think, for myself, this understanding right here is the real key to why that ratio is equal to 1, because that length and that length get closer and closer. So you can prove it to me another way, but this is the one that really convinces me of it. So sometimes one way provides more insight than others. So anyway, now how does that apply to differential equations? Let's go back to the one that we had at the beginning of chapter 3, which was the derivative dy dx is equal to x plus y. Okay, that was a linear first order differential equation. It was not separable, so we had to come up with a new analytical way of solving it, which we did, and we got the solution. Recall that the solution was y is equal to c e to the x minus 1. And then depending on the initial condition, you get different values of c there. Okay, that was the solution. But anyway, suppose we didn't know that. We do happen to know it because we solved it. But suppose we didn't. In particular, if we had this problem right there instead, this would be one that would not be a first order linear. It would not be linear because you have a y squared. So there's no way that we have to solve this one. It's not separable and it's not linear. So this particular one right here could not be solved by either of those methods, and we're pretty much stuck. So with this one right here, we would have to use some other method, such as the one that I'm going to show you right now, which is a graphical method. Okay, this is one that just uses a graph to get the sense of it. So we could do this one because this is one that can't be done any other way, but I'd rather do one that you already know the solution of, just so that you can compare the solutions and see that they end up giving you the same thing. Okay, so we will use this technique on one that we could do several different ways. So anyway, let's go ahead and do it. And here's the way you do it. Go ahead and just draw the XY plane. Okay, and then you just notice what this is saying. This equation is saying that we want a graph, we want a graph of a function which satisfies this. And what does it mean to satisfy this? This tells you what the slope of the function is at any point, and it says, in words, this is where verbally comes in nice, the slope of the function at the point xy is just equal to the value x plus the value y, right? Or another way of saying it is, at any point on the plane, if you add the x value and the y value together, that's going to give you the slope of the function at that point. So let's take some examples. Suppose you're at the point 1, 0 right there. Okay, x is 1 and y is 0. So if x is 1 and y is 0, that means that 1 plus 0 is 1. That means that at this point, the slope of the graph would have to have slope 1. So all I do is I just draw a little tick mark right there, which has slope 1. And I'm off to the races. Let's try another one. Suppose we're at the point 1, 1. I'm sorry, 1, 0, 0, 1, 0, 1. Now what? The x value is 0. The y value is 1. Add them together and you get 1, which tells you again that the slope of the graph at that point is also going to be 1. So I make a little tick mark with slope 1 right there. Okay? What if I'm at the point 1, 1 right there? X is 1 and y is 1. That look about right? Maybe it's a little bit high. Right about there. What does that tell me? X is 1 and y is 1. 1 plus 1 is 2. That tells me that the slope of the graph right there has got to be 2. So to be 2 means that I want the slope to be steeper than either of these. Slope of 2 maybe looks about like that. Okay? Roughly. Maybe that's a little bit larger than 2. It's close. Let's make it a little bit better. About like that maybe. Okay? So I can make it a little bit better than that yet. It's hard to get it just right. There, that's about right. Okay? Steeper than these. Okay, so we could keep doing that over and over again. Let's take the easiest one. If x is 0 and y is 0, then the slope there would be 0. So right there, the slope is 0, which means the little tick mark looks like that. And should we do one other one? If x and y are both negative 1, so that you're right there. Okay. Then the slope there is going to be what? Negative 1 plus negative 1 is negative 2, which means it's going to have a slope kind of like that. Agreed? Something like that. Because that's going to be down just a little further. Something like that. Okay? So we could go kind of in a hodgepodge, haphazard way like that, but let's be a little more systematic with it. Let's do it this way. Let's first ask the question, where are all the points on the plane where the slope of the function is going to be 0? That would be where x plus y is 0, which of course, if you solve it for y, means that y is equal to negative x. Agreed? And that's just the line bad. The line y equal negative x looks like that. So along that line, the slope of the graph is always going to be 0. It's a little bit better. So the slope is 0. So let's put all these little straight tick marks there that are horizontal, meaning that along that line, this one of course we already had, the slope was 0. Okay? Well, let's continue. What are all the points along the plane where the slope is equal to 1? That would be where what? Y is equal to 1 minus x. Agreed? And that's going to be a line with the same slope as this one, but it's going to have a y-intercept of 1 right here. So it's going to be a line parallel to the previous one. It's going to look like that, and along that line, the slope is always equal to 1. I already have that one. Looks something like that. Okay, let's find all the points on the plane where the slope is equal to 2. Again, that's going to be a line that's parallel to these others. It's kind of like that. And there the slope is always equal to 2, so it's going to be even steeper than these. Something like that. And you could keep going, 3, 4, 5, and so on. Let's try a couple negative ones. What about where the slope is equal to negative 1? That would be where y is equal to minus 1 minus x, which is the line like that. And notice along that line, the slope is always negative 1, which means that the slope is always going to be right along, basically along this line itself. So all my little tick marks, all my little slope marks are right along the line itself. See that? So they're going to go just like that. And finally, let's do one more. X plus y is equal to negative 2. Which means that y is equal to negative 2 minus x. So that's going to be a line like this. And there the slope is negative 2, which means the slope is steeper than that line. Oops, let's see. It's also going to be negative. Yeah, that's right. So they're all going to be steeper, and they're going to be negative, so they're going to be going down something like that. Okay? So there they are. Okay, so what do the solutions look like? What do the solutions of this differential equation look like? What do the graphs look like, the functions look like that satisfy this? Well, what you do is you just think of drawing a graph where at every point along the graph, it's got to, the slope of the graph has to be the slope of this little tick mark. So one way of thinking about it is it's kind of like you're a little ball or a bubble in the water. And these little tick marks tell you what the direction of the water is, and you want to know what direction is that little bubble going to go as it goes along there, because it has to follow the tick marks at every point. So, for example, if we start right here at this point, which is 0, 1, notice it starts here as it goes. Of course, we only have these tick marks every spaced out by 1, but there's tick marks all along the way. And so if it follows these tick marks all the way, it's going to do something like that. Keep going steeper and steeper as you go. In this direction, it's going to be less steep as you go. Right there, of course, it crosses its level right there. And then it starts becoming a negative slope and gets closer and closer to negative 1. If you think about it, there's no way it's ever going to cross this line, because as it gets closer and closer to it, the slope keeps edging in that direction. Just like, again, you have water where there's a stream and you're going like this, you're just going to get asymptotically closer and closer and closer, but never cross it. So there's the graph. If you think of, this is where, by the way, it would be kind of nice maybe to have a different color. Let me choose blue here. See if this blue shows up as blue. Does that show up here? Let me grab a red one quickly, if I may. Okay, so here's one. Right there. And then, of course, if you have something on in this stream right there, it's just going to follow the stream. So there's graphs that start right there. And then, if your initial point is right here, what's going to happen? You're going to go down and keep getting steeper and steeper in this direction. So going to go down steeper and steeper. So you have different kinds of solutions depending on what your initial values are. I think if you recall, the one that we did in section 3.1 was started at the point y of 0 was equal to 5. And so we started up here, and that we had a graph. I think the graph was 6 e to the x minus 1. So if you go to Decimus and just put in 6 e to the x minus 1, you'll get a graph that goes through the point 0.5 and will look something like this. Give it a try. Okay, if there's your initial condition, recall what we did. Here was our solution. You're going to get a graph very much like this. If your initial condition had been y of 0, if x is 0, y of 0 is equal to -3, then you're going to shoot down like that, and your graph is going to be one like this. Okay, and finally, if it were y of 0 is equal to -1, well, notice if y of 0 is equal to -1, then if you stick in a 0 for x, you're going to get y of 0. Let's just do it here. Y of 0 is equal to -1. That's going to be c e to the 0, which is c, minus 0 minus 1. So c is going to be 0. So that's just going to be the line minus x minus 1. So if you start on this line any place, then this part goes away. C is equal to 0, and you're just going to be at -x minus 1. You're going to be along that line there. So there's all your different kinds of graphs depending on what your initial conditions are. So go ahead and try, as I say, graph some of these with Decimus, taking different values for C. Go ahead, in fact, just try this on your own. Let y of 0 be equal to 2. Let y of 0 be equal to 0. Try that one. See what happens. Let y of 0 be equal to -1. That's this one right here. And let y of 0 be equal to -2. And so for each one of those, find out what your value of C is here. And then go ahead and, once you have C, go ahead and graph the function using Decimus, and you'll get these various kinds of graphs. Okay? So as I say, for this particular problem, we didn't have to do this because we already know the solution. But if you had had a y squared there, or a square root of y, or a y cubed, or a 1 over y, anything that made it nonlinear, then we would not have been able to get this solution, and we would have had to rely on some sort of a process like this in order to get the answer. And this is how computers do it. If you ask a computer to give you a solution to a differential equation, it might not be able to give you an analytical answer either, and so it will just give you a graph. And the way it does the graph is just by basically going through this process where it just follows along and just makes sure that the graph follows the slope marks. Okay, so that's the idea. So that's 4.1. In the next section, we're going to do a numerical method, okay, which is going to be very, very close to this, but instead of just drawing a picture, we're going to actually calculate numbers. And it's very, very similar to the same idea, but I'll use a different video for that one, just so we have a video for every section. Okay, very good.